so I want to start by thanking the organizers for inviting me. It's really been a really interesting workshop, and I really enjoyed seeing all of these works. And it's very good that I'm talking today because I can basically skip almost all of the introduction because everyone has explained really nicely all of the central concepts. And it's going to be a relatively, let's say, theoretical talk more than I usually like to give. So I included some stupid jokes so that at least you might have something that might be interesting. So just very quickly, in case you have the same problem that I have, that each one of your collaborators likes to either use wave numbers or frequencies or energies. I have this small tool on my webpage to convert and to check for cavities, whether you're on the strong coupling regime or not. So using Haller's unit converters, this is similar, but kind of more focused on this topic if you want to use it. So kind of what I'm going to talk about today is cavity-modified material properties that we've heard a lot about. So kind of coming from, or at least having done some nanophotonics over the last decade or so, there usually we think of kind of using materials to control the flow of light, and in some sense this is inverting the idea. We're saying now we want to use light, or actually vacuum modes, to control or modify material properties. And we have cavities that modify the electromagnetic environment, like the duck cavity that Mohammed actually introduced. And we know that these can lead to effects such as strong coupling and polariton formation. And so kind of these developments have led to new fields of research where we have been and need to combine nanophotonics, quantum optics, condensed matter physics, chemistry, etc. So, and in some sense, there's many different ways to kind of distinguish the different things that are done, but kind of what I want to focus on is the distinction between, in some sense, modifying excited state properties, where there's actually a huge amount of experiments, where we have a cavity mode that is resonant with some excitation. I get strong coupling, I get polaritons. I have the very nice property that polaritons are hybrid light matter quasi-particles, so they really have mixed properties, and I can do things like exciton polariton condensation, polariton transport, photochemistry. Joel discussed it. That's also not always kind of trivial. And then we have kind of the second big topic that we've heard quite a bit about already is to modify ground state properties, where most of the work that exists, I would say, is theory. It's proposals of trying to modify, in some sense, low energy properties such as superconductivity, ferromagnetism, ferroelectricity, molecular ground states, and where I don't necessarily need to be resonant with an excitation, or many times I'm not, because I'm exactly talking about low energy properties. And that's in some sense very related to ultra-strong coupling, and also very closely related to work that has been done for decades in the context of Casimir-Polder physics and dispersion forces. And this is actually what I'm going to be focusing on today. So just as a very quick overview, although we've seen this many times, kind of the regimes of light matter coupling, if I take the simplest system, or a two-level system inside a single mode cavity. I have my Hamiltonian two-level system. The coupling, as we've seen, is in this case the dipole with the single photon field strength, or if you want to call it the vacuum one, it's the same thing. We know it goes proportional to the inverse of the mode volume. And if I'm in weak coupling, I get the Purcell effect. I just modify the radiated decay. If I'm in strong coupling, I get the Rabi splitting. I get the polaritons that are superpositions. And for this, I need the interaction to be faster than the decay. And if I reach ultra-strong coupling, which means that, as we have seen, the coupling strength becomes comparable to the frequency of the system, where comparable, and usually people start at 0.1. If you reach that it's really the same, you can call it deep strong coupling, etc. And what you start to see is that you get ground state modifications. So your ground state, kind of here to lowest order perturbation theory written down, gets stressed by these states that contain photons and also contain excitations. Usually people are more excited about the photons, that my ground state contains photons now. And one important thing to point out here is that the ultra-strong coupling modifications are really have nothing to do with resonance. If I look in this very simple model, what I see is the sum of the frequencies, not the difference. So it doesn't matter whether my cavity is actually resonant with the excitation up here, or whether it's somewhere up there, or whether it's somewhere here. I get, of course, a slightly different result, but it's not really a resonant effect. What that also means, and I think a lot of people are aware of this and have been taking this into account, is that it's very hard to say that I should do a few mode approximation. I have to be really careful because I don't have resonance. Usually my reason for getting or treating just a single mode or a few modes is that I have resonant effects and then clearly I select the mode. But for these ground state modifications, I don't really have that. So I have to be really careful, and I will show that basically I think it's a much better idea not to do it. And in some sense, another thing that is very well known, kind of exactly this effect, the ground state energy shift, if I treat it within perturbation theory and all modes, I get back just the standard Casimir polar physics that has been done for decades, and people also use kind of to trap atoms and so on, which I actually did when I was here as a postdoc with Michel Lukin. And so that was already basically my whole introduction, and I'm going to talk about two projects now. The first one is exactly this collective cavity-mediated interactions, which was done mostly by Petros, who was a postdoc in our group, in collaboration with Akash and Francisco, who are professors in Madrid. And then I'm going to talk about a project where we looked at kind of in the single emitter strong coupling regime, can I really access a non-perturbative regime, kind of go beyond perturbation theory? Are there any cavities, and what are the requirements that I need to be able to access that? That was actually a project led by Peter Babel, who just moved to Munich, and by Theo, who was a postdoc, PhD student in Madrid, is now a postdoc with Peter. Okay, so now we're going to talk about, in this first project, this collective low energy effects. So now we're going to think only about low energy properties, if you ground state, or low energy excitations. And the question is, how does the cavity really affect the effective low energy Hamiltonian? Can it induce, for example, long range order, phase transitions, etc.? So I'm going to start out with a few assumptions, which is basically I want to do it very generally, so I cannot do something extremely precise. So I'm going to have a few simple things. First of all, I'm going to assume that my system can be split into units. They don't necessarily have to be emitters, but I'm going to call them emitters usually. Certainly they don't have to be two-level systems. Actually, I'm interested in kind of the low energy physics. I assume that all of the internal energies that I care about for now are much smaller than the relevant photon energies, so I don't really have resonance effects within the subspace we care about. Although later on I will mention that we can think about using mediator modes that are resonant with the cavities. For example, if we think about something like spin-phone and photon coupling. So kind of the Hamiltonian I start out with is the free space emitter Hamiltonian, plus in this case a single cavity mode, and then the dipole coupling with the mode of the cavity. And as we've seen already several times, if I now integrate out the photon mode, exactly I want to get the effective low energy Hamiltonian. I can do this with Schrieffer-Wolff, or with the path integral formalism, or Hebb and Lieb. So there's kind of many different approaches that in the end all lead to basically the same result, which is that I get some interaction Hamiltonian between these emitters or units that contains the dipole interaction mediated by the electric field at the position of the two different units that I'm considering divided by the photon frequency. Okay, but again, here I don't have any resonance effects, the same as in the ultra-strong coupling, right? So I really don't know that I can restrict it from the beginning to a single mode. I would have to have a really good argument for it, or let's say, if I sum over all modes, at least I know I'm not doing anything wrong. So the strategy to use is to sum modes and check convergence, and we were motivated by an experiment by Thomas Ebbelson, which is a more or less simple multi-layer geometry. So we started actually trying to do this, find the modes. Here you have in a polymer system in polystyrene. You have these 4 nanoparticles on top of a metal mirror and a silicon substrate. And you ask your postdoc to look up the optical constants and so on and start looking for the modes, and you work for quite a while and you get this huge zoo and you start summing over it and you realize it doesn't converge, nothing really works, and we're going to need more modes, so we keep going on. Yeah, we ran into a problem. Johannes didn't think enough. So, yeah, basically we realized this was not a good strategy. Let's go back. We kind of, if you think about it a bit, you realize an explicit calculation of all modes, especially if you need them to be quantized and you want to represent a realistic geometry, is really only possible for very simple models, or very simple geometries. For example, at a Reaper cavity, if you assume perfect mirrors, you know all the modes. Actually, you have the problem that it's not really a physical system because the mirrors in reality are not perfect. At high frequencies, they always disappear. And kind of more fundamental problem that you have is that standard quantization procedures in quantum optics with the dielectrics fail if there are actually material losses. So you have to be very careful and think about how do I normalize my modes and so on. The underlying problem is that Maxwell's equations become non-Hermitian if I have losses, and then if I lose my normal quantization rules. So now if I think about exactly I want to do something general, and I realize, well, I have Kramers-Kronig relations, those actually tell me that all materials are lossy. I never have no losses. I mean, I can have some frequency regions where there are where there are low losses, but in general, any material that has any frequency-dependent dielectrics, or any material, will also have losses. And if I want to sum over all modes, I'm going to have to solve that problem. So we need a way to obtain all modes for arbitrary geometries. I want to be able to do it for a duct. I want to be able to do it for nanoparticle. I want to be able to do it for anything. And fortunately, much smarter people than us have already solved this basically. And the strategy to do it, for example, Angel was also showing that they are now using, is what people nowadays call macroscopic QED. So what's the general idea? I just want to give a very quick introduction about that. So we want the quantum description of light-matter interactions in basically arbitrary structures. First, we might have to think a bit about what do we really mean with light and matter. And in traditional quantum optics, this is relatively obvious. I can just think of light bouncing around the mirrors. In the middle, it's clearly light. Right? And the mirrors just give me boundary conditions. I get discrete modes. The losses are mostly small perturbations. But what we want to think about, especially coming kind of from nanophotonics and plasmonics and so on, are systems where I have really metals, like the sub-wavelengths, terahertz antennas of Jerome also fall into this category, where what really is happening, even if I can understand everything with Maxwell's equations, is that the charges are moving around. And so what I call my light modes are actually mostly electrons moving around. The photons, what I call photons, are really mixed light-matter excitations. For example, surface plasmon polaritons, and I have material losses and radiation losses that are often very large, and they're really important, so I have to take them into account. So how can I do this? Well, macroscopic QED follows a very simple strategy. It's basically saying, I want to have some parts of the system that I want to treat exactly, up to whatever level of exact you are interested in. For example, as Angel was saying, you can use DFT, you can use models, whatever, quantum chemistry, big calculations, whatever you want. And then I take the rest of the system that I say I call my cavity, and what I basically assume, the only thing that I assume is that it's described a linear response. As we have just heard several times, Joel was also discussing this, any big enough system becomes linear, at least to a first approximation, and we're assuming that we don't have nonlinear effects within the cavity that are important. So that means I can describe that system through macroscopic electromagnetism, Maxwell's equations, for example. If I make the local approximation, which I don't really need to do, but I can, it's fully described by the permeability and permittivity of the material. And what I do then is to basically set up a system of coupled harmonic oscillators. I know my system is linear. I know harmonic oscillators are linear. I just need to find kind of a collection of harmonic oscillators that reproduce Maxwell's equations. And then I can quantize it. That's basically the whole idea. And the very important kind of conceptual point here is that I know that I can actually represent dissipation simply by an infinite path of harmonic oscillators. So I can treat a Hermitian system that will have dissipation, and I get rid of the problem of the losses because formally my system is Hermitian. I just have internal losses into a path that is just another set of harmonic oscillators. I can diagonalize this, and kind of the nice thing is exactly because I set it up to reproduce Maxwell's equations, the solutions I can just write as the Green's function. We know the Green's function is exactly what solves Maxwell's equations, the dyadic Green's function of Maxwell's equations. And then I can quantize it, and what I get is a description that basically describes the quantized medium-assisted field as a collection of bosonic modes of harmonic oscillators. And this is the nice thing about this, that it's really completely general. The final result for any system that you put in is simply that you get a huge collection of harmonic oscillators, one at every point in space and at every frequency and at every direction, and either electric or magnetic excitations. They are commuting with each other, and I have, for example, I can express the electric field operator as a sum of all of these. So I see Jerome already laughing and saying, Johannes, what are you telling me? How is this an improvement? I mean, you're now telling you have a huge amount, yes. But the nice thing is, all the information is collected in the Green's function, and we're going to see that there's very nice fundamental properties of the Green's function that I can use, and actually I'm going to show that, for example, the system we were treating, this huge sum basically drops out completely, and I get a very nice simple result. Yes?
In what respect is this QED?
Because I've quantized the electromagnetic field.
No, it's the Coulomb interaction we know is QED, but I can just, from purely classical arguments, get the Coulomb interaction.
Sure, no, but here I do have the full electromagnetic field of free space plus the material. So I have, basically the reason why this is not as trivial as I'm making it sound is because you have all the usual complications of QED, of quantizing the electromagnetic field. You have to be careful that you have the constraints and the divergence and so on. But that's all the same as in free space, basically. And then you couple it to the materials, which is where you have to be careful with that you have the internal losses and so on. But in the end, it's still a system of linear harmonic oscillators, because that's the only system that is fully linear, and we want a linear system. So that's, in one sense, it's kind of trivial, as you say. I can say, what linear system can reproduce Maxwell's equations? Well, a system of perfect harmonic oscillators described by the Green's function. That's the only thing that can do it, but you have to go through a lot of work to actually get it. Yeah, and as I was saying, all the information is then encoded in the dyadic Green's function, which just shows up here. As I said, as it should in any linear system, we know that reproduces the full response of the system. So the question is, have we gained anything? Well, now I can go to this expression that we had. I've written this out so we can treat kind of the field-dependent part of the interaction separately. Now the sum over modes that here still look kind of manageable, which is the single index n, actually becomes an integral and sum over everywhere in space and over the frequencies we're going to ignore for now. I have to sum over these different components, P, which actually electric or magnetic excitation, and I have the Cartesian directions. But I have this really nice identity that shows up basically always in microscopic QED, that if I have this integral and sum over the kind of internal points of two Green's function, I get back just the imaginary part of the Green's function at that same frequency from point R to point J. So integrating over that point S, summing over these integrals makes a huge amount of my sum and so on drop out. And I get as the effective interaction here a much simpler expression where I have just a single frequency integral, and the quantity that shows up here is actually known as the so-called cross density of states. It's basically telling me what number of states connect my point Ri with my point Rj. So you can already say, okay, this looks a lot nicer than we might have expected. Yeah.
Yeah. So my question is, so each dipole has some internal energy,
Yes.
like scale, but the Green's function with which they interact, it kind of doesn't have this information.
Yeah, because as we said, we were ignoring those internal energies as is usual, kind of exactly in this field. We are assuming that we want to look at low energy properties that are lower than any of the relevant frequencies within the Green's function. So this is exactly what people in the field use when they integrate out.
So is it equivalent to electrostatic limit or something?
This is exactly the next
Okay.
step. So this is what we will see right now. Okay. So now I have this integral that still, you kind of say, okay, this is maybe much simpler than what we used to have, but not completely trivial. But then we realize, well, we actually know also completely generally the only pole of this integrand of omega times the imaginary part of the Green's function is at omega equals 0. So I can actually perform this integral analytically with contour integration, and I get back a final result that is exactly simply electrostatics. So all I get back from kind of integrating out the photon modes is the electrostatic interaction, and this now includes both the free space and the cavity-mediated electrostatic interaction between these units or dipoles that I assumed in the beginning. So what this is telling me is that really I should not be using few mode approximations. This is actually a much simpler result and much more intuitive, and includes all the modes automatically.
But for resonant things?
Yeah, of course. This is only of resonant. Resonant things, but I'm not saying that polaritons are explained by electrostatics. I mean, I'm talking about low energy physics.
Well, the fact that this is electrostatics, we just see from the pole structure of the Green's function, and has only one pole at omega equals 0. What's
the omega times the Green's function always only has a pole at omega equals 0. So this is not because I'm assuming that there are no resonances or whatever, it's just that all the resonances are below the real line. This is the general. Yes.
What's the difference between G and GP?
So yeah, okay, this is a detail that I didn't go into. What shows up in the expression for the electric field is GP in the for the electric field. It contains a prefactor of the dielectric of the local dielectric constant and things like that. So this one is not just the normal Green's function, and the one without the sub P it is. So if I look at the magnetic field, for example, it's the rotation of the Green's function and so on. So these are details of the theory, but here this is just the normal Green's function. He was first.
So I think I'm just a little bit confused. So you said this is essentially electrostatic dipole-dipole interaction, but you're integrating out all the transverse modes?
Yes.
So it shouldn't it be magnetostatic?
I'm integrating out all the modes. So both the longitudinal and the transverse modes, and I have electric dipoles, so it's electrostatic. If it was magnetic dipoles, it would be magnetostatic. But I started out assuming electric dipoles. It's not all the steps apart from that should be the same, but it's the static response of the electromagnetic system. Sure.
Yeah, well, maybe you explain later, because that seems like the cavity doesn't do anything after it.
Well, no, the information about the cavity is in the Green's function. So exactly. So within these approximations, I just see the static response, which in some sense is trivial because I assumed from the beginning that the system, I'm looking at low energy properties where I say that the frequencies are negligible compared to the other things that I'm looking at. But that's often what we want to do.
But you have to also subtract off the back. I mean, these modes are fluctuating even in vacuum without the cavity.
Yes.
And you can evaluate the same Green's function in free space.
Yes. So this includes the free space. If I want to look at I equal j, I have to be careful because it is the usual divergence that I have to renormalize, etc. And the strategy to do that is exactly to use that the divergence comes only from the free space part, so I can just subtract it out because I know that's already there in my bare emitter.
So you already are doing that here?
Yes, yes.
Okay.
Well, here basically, yeah. We're mostly interested in the interaction. There you don't have that problem. So there it's just you get the sum of direct dipole-dipole interaction plus whatever the cavity gives you. Yeah, so as I was saying, in some sense we should, or at least could have expected this because we kind of implicitly at least assumed it. In fact, in the derivation that we used with the path integral formalism, you never really explicitly say that the frequency is zero, but in the end you realize that that's implicitly there. The advantage of this is that it's of course very easy to understand intuitively. We know how electrostatics work. The disadvantage is that it kind of tells us that we have some limitations in what we can do.
Because it has been a long time since you saw the original Hamiltonian. Did you also have the counter rotating the
Yes,
times
yes,
there?
of course, yeah. Otherwise, so it's not rotating away from us. It was, I didn't even specify what the dipole
In
is. It's
macroscopic
just a
QED,
dipole.
you don't have any photon-photon interactions, or do you?
No, I assume it's linear. I assume my
You assume it's
cavity
linear.
is linear. So then, otherwise, I would, well, that would be nonlinear optics. Basically.
But we know that in some cases they should sort of be around, let's say, sort of interactions.
There are, of course, interactions, but I don't see of any kind of cavity where I try to modify the material that there should be.
I have a question. So if I have like, say, dielectric equation or something, which is like a so then
So
people
here
don't
we
microscopically
specifically
for
don't
that.
have gain.
But suppose
Yes.
is it easy to add gain in this formalism?
You can do it.
But then you can
You
also
have to be somewhat careful because gain in reality always means that you have a non-equilibrium, so you're actually pumping the system.
Yeah.
And if you just represent it through gain, you will get kind of an explosion of the energy. You will get pump infinite energy into it. Basically, you get poles at above this, the real line, and then you have to be careful. So I'm not sure these arguments would directly apply. I haven't looked into it.
But for example, are there efforts to extend macroscopic QED with, like, say, materials with fair nonlinearity?
Sure. I mean, yes, yes. In fact, we are looking into that as well right now. There's a few other papers. But this would be saying that I use nonlinear optics in the cavity material. Here the idea would be that all the nonlinear, all the interesting physics is in the material, and the cavity is just this type of metal that gives me the modes. Yeah, I'm not trying to do nonlinearities in that cavity. So another idea that kind of we had was, what if instead of using direct coupling between the low energy parts of the electromagnetic field, where it's obvious in some sense, in hindsight, it's obvious that it's electrostatics. What if we use a higher frequency mediator mode, for example, an infrared active phonon that spins can couple to, and then those phonons can couple to the photons, and then this phonon-photon coupling can be resonant. Maybe I get something more than electrostatics then. No, sorry. Yeah, we were also disappointed. In the paper we discussed this in a bit later to show it, but in some sense it's again somewhat trivial because it's just another boson mode that I can see as part of the whole bath that I'm coupling to, and my ground state properties are still ground state properties. So, kind of, to summarize this first part, our first reaction basically, let's put on masks and go to Iowa into the cornfields and sing sad songs. But then I remember, no, I'm actually not from the US, I'm from Vienna, and in Vienna, for almost a century, we have said the situation may be hopeless, but it's not serious. We just keep going, right? So, in some sense, what our results highlight is the necessity of taking into account really all modes, if I want to look at non-resonant effects. Macroscopic QED really provides a very nice framework for this because you can use all of these general properties of the Green's function, and you automatically avoid all of the problems of having to quantize yourself and so on. All of this is in the Green's function, so I really recommend doing that. And for this specific case, we found that it's all electrostatics, but as I said, this also gives very intuitive pictures and gives probably new ideas of how we can make a system that really will change stuff. And of course, we did have several approximations there, so in some sense what we're doing here is a baseline for more complex situations, but it's a baseline that I have to take into account. So I will always have this, and then I can have corrections on top. I think that's what we should do. I also want to point out quickly, we used here for simplicity kind of point dipole interactions, but really all the derivations that give me this final result do not depend on that. I can do macroscopic QD beyond dipole interactions. I can use the polarization density directly. I can use quadrupoles. I can use magnetic interactions. None of the steps here depended on that. It's kind of on the outer part, but the Green's function inside that I integrate out, I will still get electrostatics. So at least that doesn't directly solve this or give me more. But for example, one very interesting application that we found is if we assume a system of ferromagnetic nanoparticles, so we assume kind of particles that each one have already from the beginning a large spin, and I have spin phonon coupling with infrared active phonon modes, exactly this mediator setup that I looked at. And I write down the spin phonon interaction. This is a quadratic term in the spin. The beta here is the phonon. And I can now go through my formalism, I integrate out the photon modes, and I find that I get an effective biquadratic interaction between the spins of these nanoparticles. That is exactly given by the electrostatics. And the interesting thing, so this is really Akash who comes from magnetism, as he pointed out, is that since this is quadratic in the spins, it means it's not sensitive to the orientation, it just is sensitive to ordering. So I have some kind of unconventional magnetism between the spins of these particles, where I promote, depending on the sign of this effective coupling, ordering or anti-ordering, but it's not the directionality that is effective.
Sorry, how do you couple the IR phonon to the spin upwarder?
So this is spin phonon coupling, is basically magnetoelastic coupling.
Would that couple to Q squared typically?
Depends on the symmetry of your material. So it has to be a non-central symmetric material. Yeah. So yeah, here in the paper, that's not the archive, that's another paper. But yeah, we discussed that in detail. In fact, Akash derived the whole model because it hadn't been done for this frequency regime. And for example, one very interesting thing that you find in this case then is that you can get actually a first order phase transition from magnetization as a function of the temperature. That kind of, as you reach a critical temperature, you get a stable state where the spins are all ordered, and it's a first order transition, meaning I have a jump here. So Akash was quite excited about this. I really know very little about magnetism, but I think it's very interesting. And for example, I mean, here this is actually in free space, so it's really just completely electrostatic free space dipole-dipole interaction, but if I put it on top of a substrate with different dielectric functions, metallic or dielectric, I can really significantly, as a function of distance, modify my transition temperature. So we think that's actually could be an interesting application.
Sorry, but,
yeah.
Okay, so I'm a bit confused about this last message compared to the negative side.
No, this is the point. It may be electrostatic, doesn't mean that there's no effect.
Okay, but this was not known before.
At least I don't think anyone understands this. Okay, so if I have a few more minutes, I'm gonna...
6 more minutes, including the
Okay. We had a lot of questions. So I'm going to very quickly talk about this, which is basically saying now for a much simpler setup, single emitter, can we actually access the non-perturbative regime and go also kind of beyond the electrostatics? So again here, Alpha-Stone coupling. Is it possible to access a regime where vacuum-induced corrections really become comparable to the bare energy scale of the matter system, going in some sense beyond also these electrostatics? And for this project, we actually wanted to take not this macroscopic QED, but a simple system where we can write down all of the modes explicitly. So the first model that we looked at is exactly the cavity with perfect mirrors and an LC resonance. The Hamiltonian, and we'll go very quickly, is again a single, now we use a single dipole in free space. Now we don't neglect its frequency, so it is a frequency omega 0. Write it here. we take into account the electrostatics, so that's basically the image charges on the plates that will actually modify my emitter. I take into account all of the transverse electromagnetic modes in this perfect mirror cavity, and they're coupling through the vector potential with the emitter. And I take into account an extra LC cavity mode, where I assume that I have connected my two plates with an LC circuit, and that gives me this linear coupling, and basically this term that looks a bit like what people sometimes call the dipole self interaction is basically to cancel out the image charges that are already included in here. So if you remove the contribution of this mode to the image charges, you can remove this, but if you want to do it like this, you have to include this extra term. And now we can calculate the ground state energy shift and basically see, we do it perturbatively and see if we can get it large enough that we know that was not enough. So you get basically three effects. You get the contribution of these electrostatic effects, that's actually very easy to calculate, and it becomes, it scales as 1 over the distance to the plate, either the upper or the lower one. You don't really get anything much beyond that. You get the coupling to the transverse modes in this geometry. That's a kind of, turns out to be actually numerically or analytically the hardest calculation. It diverges, but it's actually always a small correction, because it's exactly, you have to remember this, what we said before, that free space already diverges, and what I really want to calculate is the correction compared to free space, because in free space I know that full renormalization, etc., just gives me the lamp shift, which is very small. And what we find is that this correction is always small, basically because the fine structure constant is small. So this is the dipole moment, if you want. Here we scale it compared to the frequency, and this is a number that depends on exactly where you are in the cavity and so on, but is below 1 usually. And then the cavity mode, the LC circuit, that correction turns out to be actually also very easy to calculate, and now this is just a single mode. And you get an expression that looks very similar, but the important point is that you get here, in this language of impedance, a term that is exactly the impedance of the cavity mode over the vacuum one. And this can be very large because you have an LC circuit that you can play around with as you want. And so you can actually get this to be large as long as you use a high impedance mode. Another system that we looked at, kind of, well, it's very similar, you can do very similar things, and what is more similar to what I usually work on, which is plasmons, plasmonic nanoparticles. I can, in the quasi-static approximation, calculate the plasmon modes, and I get a very similar expression, where again I can rewrite it in terms of this characteristic impedance, and the numerical prefactor, there is only order of 1, and the characteristic impedance, depending on the properties of the plasmon, the material you choose, can be on the order of 100 or so. So you can kind of beat this fine structure constant that is roughly 1 over 137. So with this approach, we can really look in detail to differentiate between purely electrostatic effects and fluctuation corrections. And the first thing we found, which is similar to things we heard also yesterday, is that if we kind of look at just the free space or the transverse photon modes, the resulting energy shifts are actually, well, the transverse photon modes are really small, and the rest is electrostatics. But if I have these LC high impedance modes, I can get strong couplings that are beyond this electrostatic effect only. And basically what high impedance actually means is that it's really not photons, in that sense it's charges moving around, which is a bit what Jerome also mentioned, the kind of what we call photons, if we actually want to have really strong interactions, are never actually photons. It's always electrons that behave collectively enough that we can act as if they were photons. And with that I'm already finished. I want to thank Petros and Theo, who did most of the work, and also the other co-workers, and thank you for your attention.
Just as a very short question, so that I make sure I understand the strength and the weakness of this main function for one. So essentially, you tell that you can leave it if you place something in the cavity, which has a nonlinearity. You allow the cavity to perturb the nonlinearity, but you don't allow a feedback from the nonlinearity. feedback to the cavity will be given only by the linear response of pulses.
No, I wouldn't say that. The material inside can be as nonlinear as you want.
And the material will, for instance, a material will perturb the modes of the cavity,
Sure.
but only the linear part of the response of the
Yes, yeah, if I want to include that,
participate
so
in
yeah.
this perturbation. The non-linear part will not participate in the perturbation.
Not in the linear modes. So
It's
that would be
intrinsically
nonlinear physics on top. That I
This
would
is
calculate
intrinsic.
exactly as the nonlinear corrections on top. If I do, and when I drive and I want to do nonlinear photon generation, photon pair generation, I could include that, but here I want to calculate the modes and those have to be.
One more question.
Sorry for the dummies. Let's say, how did then your first Green's function approach, which must be really general, and sort of was indicating only the electrostatic effect, so it prevents the impedance effectively argument, second
What the impedance is just,
No, sorry,
the Green's function contains all of electromagnetism without any electrostatic approximations. The electrostatic approximation is only in the interaction with the material system that I want to modify. So if I have a kind of the wire with the LC1, as you do, you solve Maxwell's equations and you get that's in the Green's function.
So I'm still puzzled by, on one hand, you have this correction, the first part of your talk, you have this correction where you take the imaginary part of the Green's function, go omega to 0, and let's say in the second part, in the end, the largest contribution comes from kind of an easy.
That would also be in the Green's function. It's just that there I cannot assume that my emitter is zero, kind of that my emitter dynamics I care about are zero frequency.
Okay.
So
that's it.
there we didn't do it. Yes, that's really the correction I calculated.
Okay.
So if you want, what we said becomes large in that limit is the correction because I have a frequency of my emitter. So there I'm looking at the two-level emitter. So that's the correction we.
Intrinsic frequency.
Yes.
That's actually 10 protocols because